Let's see what is the Wheatstone Bridge. The Wheatstone Bridge circuit shown in the figure 13.23 consists of four resistances R1, R2, R3 and R4 connected in such a way that as to form a mesh ABCDA. A battery is connected between points A and C. A sensitive galvanometer resistance R is connected between points B and D. If the switch S is closed, a current will flow through the galvanometer VR to determine the conditions under which no current flows through the galvanometer even after the switch is closed. For this purpose, we analyze this circuit using Kirchhoff's second rule. We consider the loops ABDA, BCDB, and ADCA, and assume anti-clockwise loop currents I1, I2, and I3 through the loops respectively. The Kirchhoff's second rule as applied to loop ABDA gives minus IR R1 minus I1 minus I2 into R minus I1 minus I3 into R3 is equal to 0. Similarly, by applying the Kirchhoff's second rule to loop BCD, we have minus I2 R2 minus I2 minus I3 into R4 minus I2 minus I1 into R is equal to 0. Current flowing through the galvanometer will be 0 if I1 minus I2 is equal to 0 or I1 is equals to I2. With this condition, equation 13.23 and equation 13.24 reduced to minus I1 R1 is equal to I1 minus I3 R3. I1 minus I1 R2 gives us I2 minus I3 into R4. Dividing the equation 13.25 by 13.26, R1 upon R2 is equal to R3 upon R4. Thus, whenever the condition of equation 13.27 is satisfied, no current flows through the galvanometer and shows no deflection, or conversely, when the galvanometer is in the Wheatstone Bridge circuit, shows no deflection. Equation 13.27 is satisfied. If we connect three resistances R1, R2 and R3 of known adjustable values and a fourth resistance R4 of unknown value, resistance R1, R2 and R3 are so adjusted that the galvanometer shows no deflection, then from the known resistances R1, R2 and R3, the unknown resistance R4 can be determined by using equation 13.27.